Hey, I've been doing this experiment. A couple days ago, I started building a new audio engine from scratch that's music first, and it's written in Rust. And I don't know Rust, so I'm kind of using this as a way to learn it a bit. I'm also using it as a way to exercise Claude Code a bit more to build a more substantial system, and just sort of validate some of my concerns about using AI agents for kind of bigger system work. And it's going pretty well so far. It's been pretty interesting. One of the things is, yeah, of course, I've learned Rust a little bit as a result, and learned some of the Rust isms um, that I think make it a pretty good candidate for real time systems like this. And but that's not really the reason for this video. Um, the main thing I wanted to show off here was this new skill that I made within this repository. And just to back up a little bit, what this audio engine is, it's called Reuben, short for Rube Goldberg. And if you know me, I've made a couple audio engines kind of similar to this. The idea being that it follows the sort of data flow programming mindset of a bunch of small operators can come together to make complex behavior, and extrapolating that out, a bunch of small operators can really come together to make any complex behavior. And so that's how I like to build music systems. And I've written a couple similar music systems myself in C++. I've worked on a couple commercial engines, and and the thing that I've always wanted is for it to be really lightweight in terms of developer experience. So if I want to extend it um, to do something new, I want that experience to be really quick, because I think the more extensions that are made to systems like this, the more powerful those systems become. So serving that, I just got done making this patcher skill. And if you're familiar with Max or Pure Data or Metasounds or like similar audio patching environments, this system is very similar to that in that uh, you have a bunch of operators, and then from those operators, and those operators can be things like math or oscillators or sequencers or whatever else. From those operators, you can compose instruments, and the way that those instruments are composed is by connecting together a series of nodes. So, like if we look at one simple example, we've got a sampler arpeggio. So we got a sampler operator, we've got a voicer operator, we've got a sequencer, clock, output, and those connections between the clock and the sequencer and the voicer and the sampler are all defined right here, and some parameters are defined. This system talks OSC by default. So internally, the message system is OSC shaped. But also, it means that when you're running one of these instruments, you've got an address schema based on these instrument patches, and these instrument patches can be nested, so you can, they're recursive, so you can nest these as an operator within another instrument, and address them in such a way that you can get at every parameter externally from something like Max or Touch OSC or a command line app or anything else that can send OSC over a network or over a local machine or over USB or whatever else. So yeah, too late to make a long story short. I just wanted to show off this patcher skill real quick. So what I did is I made this patcher skill that lets me say stuff like make a plucky bass synth that walks minor arpeggio up and down. Add brightness control to the synth. And what's a brightness control? Well, it's going to figure that out. So let's see what happens. This is going to take a minute to work through the process. So it's got its own sort of validation loop of figuring out how to make the thing in the first place, making the thing, then validating that the thing generally works. And maybe a later feature will be actually validating that the thing makes sound. But of course, not all these patches are going to make sound. That's not the success case for every one of them. So I didn't want to bake that in just yet until I kind of figured out what does end-to-end testing look like in this thing. But anyway, it's going to go through that loop a little bit. And the audio engine itself has some validation API that the humans can use as well as the AI agents. But because I'm building this sort of I don't know, AI agent first is maybe a good way to put it. I am working on features with a mind for everything being extendable by AI agents. So I'm trying to build a set of skills that makes it so a human can say in natural language, like, here's how I want to expand the library, do that, and make it as easy and token efficient as possible for the agent to do that. So yeah, it's finished here, and as you can see, there's the JSON file that's defining the patch for the instrument, and all its connections and its parameters and stuff like that. So that brightness control I was talking about, you can see here that it's got a map node, and a map operator just says, like, take an input and then map it to some range on the output. And we're kind of reusing those. They're a little overloaded. We are reusing those in here for meta parameters. So if I say, like, I want a single parameter to fan out to multiple other parameters, then and be remapped in different ways, I'm going to take a map node on the input and call it something sort of human readable, like brightness in this case. And I've actually I've started calling them good buttons, because I had a friend who was a performer who used to just say, like, the best way to do a live electronic music performance was to make a controller that was just a bunch of good buttons, so you could hit them and it would work. So I kind of stole his term, which I like. But anyway, so it made this brightness good button, and let's see what it does. If you go down here in the connections, this is still pretty human readable. Of course, you get more complex patches, it's going to be really hard to read. But we got the brightness out port going to both cutoff and resonance on another map node. And let's see what that map node is. So map cutoff, map resonance. So it's mapping brightness 0 to 1, cutoff 200 to 6,000, brightness 0 to 1, resonance 0.1 to 0.8. Okay, so turn the brightness all the way up, it's going to have a higher cutoff frequency, it's going to have a higher resonance, so it's going to be brighter. So it figured that out all on its own, how to do that. What else did it do? Let's see. So it built a self-playing E minor bass arpeggiator, clock at 124 BPM, sequencer length 6, with these scale degrees going to a voicer. By the way, another cool thing about this system is, rather than thinking in MIDI notes, which it can do, in MIDI note numbers as pitches, it can also, and it's first class to describe musical terms in scale degrees. And there's also a whole system for doing tunings, so it doesn't just have to be Western tunings, it doesn't just have to be Western scales and chords and that kind of thing. And that is sort of first class in this system. So we can do all kinds of microtonal stuff, or so we can also just operate on the ideas of chords and scales, symbolic music language, as opposed to MIDI note numbers, which map kind of directly to frequency. So that's, I hope, going to make it a lot easier to compose music with this thing. What else did it do? It did a plucky voice, saw, oscillator, filter, envelope, with these envelope parameters, brightness control. Okay, so then if I want to play it, so what it did spit out is not actually the correct syntax for running it from the command line, and I just want to show that real quick. How do I run this from the command line? Because I always forget, so might as well ask. And wait for a response. There we go. So this is the info I wanted. Yeah, it gave me more information than I wanted, of course, but what it's telling me here is like, this is how you run the thing, and then from the terminal, since I have OSC send installed, I'm running on Linux here, I can just send OSC messages from the terminal. For now, I'm gonna skip that though. I just want to run the thing, so I'm just gonna copy paste this, open up another terminal, and just run it. We have the arpeggiator. Okay, cool. So from there, so like I said, you could use like TouchOSC or something like that. So another thing that I did was I actually wrote a control surface skill that will, actually let me just invoke it this way, make a control surface for it. And what that'll do is it'll actually make a TouchOSC control surface for me that I can open up and manipulate the patch from there. So that skill has like a Python script in there that'll make the control surface based on the schema that it currently understands. There's a couple libraries out there that will generate TouchOSC patches for you, but instead of adding that dependency, what I did was I just have a reference TouchOSC patch that's got a bunch of stuff in it, and it uses that as a reference for like what is the schema for your local version of TouchOSC. So if the schema does drift, it'll still work on your local machine. Probably not the best way to do it, but it was quick and dirty and it worked. So now it's going to ask me some questions. So let's see here. What controls should the TouchOSC surface include? I can say full, and it'll give me brightness, tempo, length, steps 1 through 6, ASDR, all that stuff. Performance, brightness, tempo, length, minimal, brightness, tempo only. I'm going to go in the middle to performance. And it's going to turn for a minute making this control surface file, and then I can show you what it does. All right, cool. So it's another thing it's going to do when it's making the control surfaces is you have the option, like I said before, all of the parameters for all of the nodes are actually exposed, so you can hit them by address from the outside. But if you're making control surfaces, it's helpful to be able to, within your instrument, say like, these are the things that we care about for a control surface. So this skill will do that for you, but you can also manually do that in your instrument files and have it just implement what you've told it you want exposed. I mean, these control surface files are really useful for testing, but a lot of people use TouchOSC for live performance or for show control, that kind of thing. So it can be your kind of end goal for how your control surfaces work for stuff you're making in here. So now looks like it's done. It made the control surface. It marked the instrument appropriately. This is where it put the control surface file. So if I go and go back and run this again, and then if I go into my projects and grab this control surfaces, put base, and start running that. So actually, I'll play the step sequence here now. kind of fun because, again, I started this less than 48 hours ago, and we got to something that makes something resembling music. But not only that, as you saw here, I didn't actually touch writing any code or manually patching anything together. This was all built with natural language fairly quickly.